Hi, this should be a short video. It's going to be all about current. Before we can start to understand DC circuits, we have to be solid in our definitions of the basics. So current's going to be our first topic and it won't take too long. Current by definition is a flow of charge, and more specifically as a quantity is the rate of flow of charge. So what do we mean by that? To understand that, we need to know what charge is. And it's worth remembering that charge is a property of matter. It's a fundamental property of matter. And that fundamental bit is actually quite important. That means that charge must be conserved. So what I mean by a fundamental property of matter, charge belongs to particles. I can have a charged particle, for example an electron, and that charge is intrinsic. I cannot remove the charge from the particle. I cannot add charge to that particle. I cannot remove charge from the particle. It is fixed. So if we talk about a flow of charge, that implies a flow of matter. Something has to move. You cannot have charge just kind of on its own. It must be attached to a particle. It belongs to a particle. So charge is that fundamental property of matter. In a normal DC circuit, the particles that we consider, the ones that move, tend to be electrons. They tend to be electrons. And that's worth thinking about. Electrons are tiny in every regard. They have a tiny mass. They have a tiny charge as well. So it's worth thinking at this stage then about the units that we'll use, because that helps us with the language of this topic. Units. The units of charge, since in a circuit it is electrons that move, and each electron has a fixed charge. Every single electron has the exact same amount of charge, and as I said, that can't be increased or decreased. It can't be removed from the electrons themselves. So it might seem reasonable to use the charge of an electron as the unit for charge, but it isn't. And the reason it isn't is because they are so tiny. I like to use the analogy of either sand or sugar. If you think about buying some sugar, you never really are interested in how many individual grains of sugar that you're buying or using. So instead, you measure sugar in kilograms. You would buy half a kilogram of sugar or a kilogram of sugar, and you would use spoonfuls of sugar. You don't count individual grains. So when we're talking about flow of charge in an electric circuit, that has a similar sort of feel. We're never really interested in individual electrons. The units of charge are coulombs. And that is a capital C. Coulomb. So the charge of an electron, one electron has a charge of minus 1.6 times 10 to the minus 19 coulombs. So a tiny, tiny number of coulombs. So if we talk about 1 coulomb of charge, we're talking about a vast number of electrons. So these are the units for charge. The units of current then, since current is a rate of flow of charge, you would imagine that we would measure it in a flow as in coulombs per second. And we do. The units for current are amps. Or amperes, but normally the overwhelming majority of times people will say amps, but technically it's the ampere. Capital A. And 1 amp is indeed equal to 1 coulomb per second. It is, though, worth noting that the amp is a basic SI unit. We discovered current before we really knew what it was. So it is the amp that is a basic SI unit. So while a coulomb is an SI unit, it isn't considered basic. We consider the coulomb to be 1 amp second in base SI units. The other thing I'll say about electrons, since they're the thing that commonly moves in a circuit, it is really important to note this minus sign. Electrons actually have a negative charge, and since we define current as the rate of flow of charge, we think about how much charge is flowing. That leads to something that can frustrate people. It can be annoying, but if you imagine two sort of tubs of charge, this one contains 10 coulombs and this one contains 10 coulombs. Since electrons have a negative amount of charge, if I take a bunch of electrons from here, so many electrons that their total charge is minus 1 coulomb, and I transfer those electrons to this store of charge on the right. Well, what I'm doing is I'm subtracting minus 1 from here and I'm adding minus 1 to here, which means that I end up with 11 coulombs here and 9 coulombs over here, which means that charge has in fact gone this way. And that's a little frustrating, understandably. So electrons moving in a given direction represent a charge moving in the opposite direction, therefore represent a current in the opposite direction. So when we draw a circuit, a really basic circuit here, I've got my cell with the positive side and the negative side. Current, charge flows from positive to negative, but the actual electrons that do the moving in the circuit are flowing in the opposite direction. And that is worth remembering. Current, traditional current, conventional current, flows from plus to minus. Electrons themselves move in the opposite direction. And that's it for current. Those are kind of the basics that we need to be, that kind of need to be well locked in, so that we can kind of talk about the more complex aspects of DC circuits.